Excellent. Thank you, Matthijs. So before starting, the first question for us is really, where do we come from? And I don't mean the philosophical question, but I mean in the specific planning area, what we demonstrated in a previous work is that by configuring a domain model, PDDL domain model, you can significantly improve the performance of planners. Now, on this matter, configuration means that you can order the way in which predicates, operators, pre and post condition are listed in the domain model. And on top of that, you can automatize this process in order to identify a configuration which performs well for a given planner on a given domain. And of course, the next point is, what about problem models? Do we really care about problem models? Does that affect the performance of planners? And also, it is important to take into account the fact that the configuration of a problem model is slightly different from the configuration of a domain models, in the sense that you have less information which are available, so you only have facts of initial state and facts of the goal state, but on top of that you have to do the configuration online. You cannot configure the model offline and then start solving it, because you will lose all the performance improvement that you can gain. So what we were thinking about is, instead of finding something which is domain specific, so that you have to re-encode or where you have to modify the code for each given domain, let's think about a technique which can exploit general information about the problem, so it is domain independent in some extent, and you can then use it for domain specific configuration or for domain independent configuration. And we found out that the planning encoding graph is a quite interesting way for representing the problem and for extracting information from the problem. So the planning encoding graph is, at the end of the day, a directed graph in which, let me try if it works. Yeah, great. So in this example, let's say we are in Bloxford. So for generating the planning encoding graph, you put basically the three objects, A, B, and C, in the middle. And then, let's say we focus on the goal state. For each predicate which is in the goal state, so in this case only the on predicate, you generate a new node, and this node is then connected through arcs to the object which are part of the actual fact. So in this case, for the goal on AB, you have the node on labeled G, because it's part of the goal state, which is connected through this arc to A, and then A is connected to B through this arc. And in this way, you can create, in a domain-independent fashion, graphs which can represent problems, and that to some extent show the topology of a problem that you want to solve. And you're not making any sort of assumption on the domain structure. And which sort of information can you then extract from a planning encoding graph? Well, this is the full list. I'm not going through that, but it's just for saying that we are analyzing the graph quickly because you want to do that online, and we can extract up to 13 different features that can then be used for the optimization of a configuration. And so now we got the features. How do we perform the configuration in an automatic way? So for each of the feature, we generated a continuous parameter in the range of -1 + 1. And on top of that, we added two additional categorical selectors. One that you can use for linking the ordering of the initial state and the ordering of the goal state. So you exploit the same order for the facts which are listed in initial and goal state, sorry. And the B, a categorical selector that allows you to decide if you want inertial fact to be on top, on the bottom of the list, or decide basically that the fact is inertial, does not matter for the configuration. And then for each fact, you evaluate its ordering score, which, as is shown here, which is basically just the sum of the weights of all the parameters which correspond to the value also of the feature that you have extracted, plus the inertial fact. Once you have the ordering score, you can then order all the facts accordingly. And the value range is in the area of -1 and +1, because this means that if you give to the specific feature a positive value, you are believing or you are indicating the fact that this specific feature is important, and you want to reward facts that show it. While if you go into the minus area, you are basically listing later the facts that show that specific feature or a high value of a specific feature. And a very easy example is, going back to our beloved blocks world, is let's say that we have this problem, which is described as that initial state, and the planning and coding graph is shown on top, and what we want to do is to order the facts following the total number of arcs that they show in the planning and coding graph. So, for instance, if we focus on the on-CA fact, it has a total score of 11, because the on predicate has 3 arcs, so we are considering, in this case, for this specific feature, we are considering the on which are shown in the initial state, so this one, which has 1 arc outgoing, and the on which is shown in the goal state, which have 2 arcs. So you got the, the 3 score for the on state, and then 4 for A, and 4 for C. You multiply that for 1, let's assume that all the other features have a value of 0, so you got your score of 11, that's the highest score among all the facts which are listed in the initial state, that goes first, and then you order the rest, following again this sort of metric. And that's the way in which you can configure basically any problem from any domain. And now that we got the architecture, of course, we try to check in an empirical way if that works or not. So we selected a bunch of planners according to the performance in IPC and according to the different techniques that they exploit, a number of domains for which we generated 500 training instances and 50 testing benchmarks, and we use SMAC for the configuration of the process, so for the process configuration. So basically, SMAC was receiving the planner, a wrapper for configuring a problem, and was trying to optimizing this configuration, minimizing the part 10, which is the penalized average runtime, which basically means you calculate the average runtime, but if a problem is not solved, you consider a cutoff time, you consider a solving time of 10 times the cutoff time. So you are basically, you have a sort of matrix which is a trade-off between coverage and between runtime, which is pretty good for that sort of configuration. And the configuration took 5 days and on one of our machines in the lab. And we set a 300 seconds, so 5 minutes cutoff time for each problem in the training and in the testing set. And for generating the pegs, we use OakPlan, which was initially mainly a case-based planner, but which is able to generate quite quickly this graph and to extract all the information that we need. And so can we improve then the performance of planners by optimizing, by configuring problem models? And the answer is yes. In this case, this is a table which shows the results obtained on the configured domains and the original domains, on the depots domain, by the 5 planners that we are taking into consideration. And for 3 of the planners, so LPG, Madagascar, and Probe, you have statistically significant improvement in terms of part 10, and an improvement of 1 order of magnitude in some cases, which is also reflected in a better coverage and, of course, in a better IPC score. And for the other planners, Llama and YASP, we don't have a statistically significant improvement, but we still have an improvement in terms of part 10 and in terms of coverage. So, yes, we can improve the performance of planners, and in the worst case, you are not reducing them. Even though you can use the same approach for trying to identify a configuration which is detrimental for a planner, but I don't know how you can use that. And at this point, we may also want to relate the domain model configuration and the problem model configuration. So in this case, we selected 2 planners, LPG and Probe, and we ran them on part of our testing set using the original domain and the configured problem model, the configured domain model and the original problem model, and the configured models, both of them. Configuration was done in isolation, so there is no interaction basically between the configuration of a domain model and the configuration of a problem model. And in these settings, we observe basically that the 2 planners has a slightly different preference. So LPG seems to be able to exploit the synergies, let's say, of the configured domain and problem models pretty well, while in the case of Probe, it seems to prefer only the problem model to be configured and the domain model to remain the same. And the other interesting fact that we can extract from this table is that if you observe improvement, or if you observe a performance of the first two rows, you see that, at least for these two planners, the configuration of the problem models, so the first line, leads to better performance than the configuration of the domain model. So despite the fact that you have less things to configure, and so you have less degrees of freedom, the problem model seems to be more important for domain-independent planners than the domain model. That was quite counterintuitive for me. And of course, then we've done all this sort of configuration. We have configured all these planners on these different domains. What is the take-home message? Is there something like a good configuration that we can use for encoding the future models? The first thing, so we use the FNOVA tool to assess the importance of this parameter that we identified. And the first important thing is that the initial and goal facts ordering should be aligned. So you use the same scheme for ordering initial and goal facts. Propositional facts which are frequently in action precondition should be listed earlier. This seems to have a positive effect on the performance of planners. And also propositional facts which are often listed as positive effects of action seems to have quite a good importance and relevance. And as a tiebreaker, what we observe is that the order of facts should follow their degree of connectivity in the graph. So what we did was proposing this approach for configuring PDDL problem models, and for doing that, we extracted information from the planning encoding graph. And our results indicate that the configuration has a statistically significant impact on planners' performance. We can gain useful information to engineer more efficient models for models of the future. And there are some also possible synergies between domain and problem models configuration that we want to explore further in the future. And of course, part of the future work is to analyze the impact of this sort of a configuration on the quality of generated plans, and the concurrent configuration of models, both domain and problem, and planners at the same time. So you have super meta configuration, which is doing everything for you. And that's it. Thank you.
Any questions?
I guess I was super clear.
Yeah, I was wondering, so you do kind of an offline phase where you try to identify what is the best set of parameters, and then you solve them. So how do the runtimes compare here?
Well, what you are doing offline is understanding the importance of each parameter, and then once you have it, it's extremely easy to create the graph and to then reorder everything. I think the creation of the graph is polynomial because what you're doing is going through the problem, and then the analysis, the sort of feature we are analyzing is in terms of number of arcs or this sort of low-level feature, so you don't need a lot of time. Of course, if the graph is huge, it takes some time, but in our experiments it was some tens of seconds or something like that.
Okay, thank you. Quick question, okay. Here you go. Yeah.
Did you consider evaluating different planners to check what makes them fail? For example, which kind of configurations would make a planner take longer to solve an instance?
No, it's something that can be done, and we've done actually that for the domain model configuration, but no, we didn't check what are the things which are not very good for planners. It can be actually quite a good thing to analyze in order to make sure what improves the performance and what is not good for the performance of a specific planner. Yeah.
Okay. Thank you.
Thank you.
Okay, let's thank him again.